Also, an object in motion tends to stay in motion unless acted on by an outside force, like my finger.
The first law of Newton's. The ball floats in microgravity. When the astronaut gently pushes off the ball, both keep moving in a straight line at a constant speed without stopping. This shows Newton's first law of motion, which says that an object will stay at rest or move at a constant velocity unless an external force acts on it. In space, there is almost no gravity effect, friction, or air resistance. So the net force on the object is zero and its motion does not change. Many people think that a force is needed to keep an object moving, but actually, a force is only needed to change motion, such as to speed up, slow down, or change direction. Because there are almost no external forces in space, objects keep moving until another force acts on them. This shows that motion continues naturally when no force acts, and force is what changes motion. The second law of Newton's. When the runner in red sees the runner in green getting closer, he quickly pushes harder on the ground to increase his driving force F. At this moment, there are two main forces on him: the forward force F, his push, and the backward force FF, air and ground resistance. According to Newton's second law, F equals ma. If his mass doesn't change, a bigger net force means a bigger acceleration. Because he increases his push, F becomes much larger than FF. So the net force grows, his acceleration increases, and he runs faster toward the finish line. So, this shows that by increasing his force, the red runner increases his acceleration. This is the reason why he could overcome the runner in green. The third law of Newton's. In this scene, two cars crash head-on, and both bounce backward with their fronts badly damaged. This can be explained by Newton's third law of motion. When the car on the left exerts a force F on the car, on the right car exerts an equal and opposite force F on the left car at the same time. These two forces happen simultaneously. They are equal in size but opposite in direction. Even though the forces are the same, the effects can be different, because the two cars may have different masses, speeds, or body structures. The lighter or weaker car will usually move back farther or suffer more damage. This shows that in a collision, every action force has an equal and opposite reaction force.